Welcome back to ECE 501B. As way of announcements, homework number 2 is due this week on Thursday. I have made available the textbook by Franks. That's on D2L, and you can find that on the content page underneath the course resources unit. And if you want to, you can access it there, and if you're having trouble, let me know. What I want to do today is sort of bring us back up to speed with where we were or where we left off by means of a very quick review from the early part of Chapter 2. Ideally, we'll finish Chapter 2 today. I don't know if that's going to happen. Maybe I'll give you some supplemental material after class or between now and Wednesday. I don't know. In terms of a review of Chapter 2 was finite dimensional vector spaces. And we started with talking about what it means to span, or what do vectors do when they're spanning something, or when you take the span of a set of vectors. If that set of vectors actually spans the entire vector space, capital V, then we say if this was our set of vectors, we would say that set W spans V. That's just the terminology that we're using. We've also talked about linear independence of vectors. We just started talking about the linear dependence lemma, and that's on page 25 of the Axler text. We'll pick up at that point. We'll talk about basis and what that means. It really means if you have a set of linearly independent vectors that also spans the entire set V, then that set of vectors can be used as a basis for your vector space V. So you have to have those two things going on. They need to be linearly independent, and they need to span all of V. That's what it means to be a basis of a particular vector space. We will then talk about, at the end, it sort of is what we've been thinking about all along, but we're following sort of the outline of the textbook, the dimension of a vector space, where the dimension of the vector space V is, if you count the number of vectors in that basis, that's your dimension. That's really all that's saying, is the length of any basis of V. Length meaning how many vectors are in that set of vectors. What's the length of that set? That's what that's meaning. Here's our quick review, just to try to bring us back up to the same location where we stopped. Chapter 2 was finite dimensional vector spaces. Chapter 1 was all of vector spaces where they could be infinite dimensional. Now we're going to specialize that to be finite dimensional. If we were talking about maybe something to visualize, which might be this three-dimensional space, the real coordinate axis, you could talk about a span of a couple of vectors in that particular space, where the span of these two particular vectors, 1, 0, 0, and 1, minus 1, are actually equivalent to the xy plane in that three-dimensional space. So that span, you could say, oh, the span, anywhere you can do with linearly combining those two vectors, that will get you to any location in the xy plane of that three-dimensional space. That's what we're meaning by span. We can also talk about when a collection of vectors, and I'm hoping that you're not getting completely confused by the overloaded notation that sometimes is used. Here, W1 represents a vector. It's not a coordinate in, let's say, this set W in a vector W. So W1, W2, W3, W4, those are 4 different vectors. That collection, or that set of vectors, we can say is W. So now you have a set of 4 vectors. And if that spans, or if that span fills the entire space V, then by definition we say W, this spanning list, spans V. That's what we mean when somebody says, oh, this set of vectors spans V. That means you can get anywhere in that vector space by a linear combination of the vectors in that set. That's what that's meaning. Relative to linear independence, we talked about what does it mean to be linearly independent in terms of vectors. Here, the A's are scalars, the V's are vectors. Symbolically, if you linearly combine n V's, and that combination ends up being 0, the only way that you can get the additive identity by this combination of V's is if all of those A's are 0, then you know those vectors are linearly independent. That's a way of thinking about what does it mean for a set of vectors to be linearly independent. That will only happen if, when a linear combination of those vectors does equal 0, that forces all of those scalars to equal 0, then you know those vectors are linearly independent. Just the opposite of that is when you have linearly dependent vectors, and that's when you can actually write one of those vectors or more of those vectors as a linear combination of the other vectors in that set. That's when you would have linear dependency among the vectors that you're working with or in your collection of vectors. In this case, I'm simply saying, oh, maybe I have a set of vectors omega 1, omega 2 through omega w, and that's a linearly dependent set. Then by the appropriate labeling maybe of those vectors, I could write one of those vectors, let's just call it omega sub m, as a linear combination of the other m minus 1 vectors. Then those vectors are linearly dependent. Again, I'm trying to just quickly get us thinking about what the concepts were that we talked about at the beginning of chapter 2. We finished our discussion partway into chapter 2 with the linear dependence lemma, and let's just talk about that now and then continue from that point forward. We had a couple of things we wanted to comment on with respect to the linear dependence lemma, and the first one, comment A, is it is possible to find an element of the list when you have a set of linearly dependent vectors. You can find an element of the list that can be written as a linear combination of the remaining elements. That's if you have a linearly dependent list. Or, i.e., that is, one element in the list is in the span of the other elements in the list. For example, suppose we were again dealing with vectors in R3 that have their coordinates belonging to the field of real numbers, R. Then you could look at this set W consisting of 3 vectors, W1, W2, W3, and maybe I've picked these 3 vectors. Those 3 vectors actually are linearly dependent because you can take 2 of omega 1, 3 of omega 2, and that actually combines to form omega sub 3. So if you can combine some of those vectors in your set to create another vector in your set, then those vectors are linearly dependent. That's what that first point underneath the linear dependence lemma was talking about or making as far as a point. Let's now look at the second comment, and now, and you could say that omega sub 3 is an element of the span of omega 1 and omega 2, if you wanted to. That's another way of describing that linear dependency among those 3 vectors, omega 1 and omega 2 and omega 3. Let's now look at this next point, let's say B. Again, we're working with a set or a list of vectors that are linearly dependent. Now we can say that removing a linearly dependent element from the original list produces a new list with the same span as the old list. So if you have a list of vectors and there's some linear dependency among those, if you remove one of those vectors that's linearly dependent, then you can keep it out of that set and still span the same area or dimensions that you were able to span with the original collection of vectors. That's all that's saying. So if we wanted to think about how we might show that or prove that, we can think of it in the following way. Suppose now to prove that we say given a linearly dependent list of vectors, let's say W equal to V1, V2, up to V sub n. And now from that set of vectors, so the V's there are not the coordinates, those are vectors again. V1 is a vector, V2 is a vector, and a vector that's in the span of this list, which we can denote by saying U is now an element of the span of W. What that means then is that we can form a linear combination of those V's to create U. That's all that means if we say U is an element of the span of W. So that means that we can write U as an alpha 1 V1 plus an alpha 2 V2 up to an alpha sub n V sub n. And obviously that's going to depend on the V's, but you can create that for some, let's say, set of these alphas. Maybe we go ahead and say alpha 1, alpha 2, up to alpha sub n. Now, what we assumed, though, if we go back, we assumed that that original set, W, contained linearly dependent vectors. And if those are linearly dependent, then we can write one of those in terms of the others. And if we can do that, why don't we just change the subscripts if we need to make V sub n be the one that we can write in terms of the earlier V1 through V sub n minus 1. If that list is dependent, then we can write in terms of the other vectors, let's say by the appropriate labeling of the V sub i's. Meaning we can say that V sub n is now going to be, let's say, minus A1 over A sub n, V sub 1 minus A sub 2 over A sub n, V sub 2, etc., down to A sub n minus 1 over A sub n, V sub n. That's really relying on this relationship saying that we can find a non-zero at least one non-zero coefficient or scalar a sub I, such that this sum a1 v1 through an vn is equal to 0, if that set's linearly dependent. We'll have some non-zero value for at least one of the scalars, the a's. So this, yes, thank you. So this should be v sub n minus 1. Yes. So this v sub n now we have rewritten, or we've expressed as a linear combination of the earlier or the other n minus 1 vectors. Now all we have to do is replace in the previous representation of u, or substitute back for this v sub n, and hopefully you can now see, oh, we've effectively eliminated v sub n, or rewritten that in terms of all the other v sub 1, v sub 2 up to v sub n minus 1. And if we collect all the coefficients, we'll see that u is now written in terms of one fewer of the vectors in your linearly dependent list of vectors. So u is now some beta 1 v1 plus beta 2 v2 plus, let's say, beta sub n minus 1 v sub n minus 1. And this is one fewer of the vectors that we started with. Which says that u then can be written in terms of v1 through v sub n minus 1, but we actually didn't really uniquely identify u. That was just some element of v, but u, or I should say u, was an arbitrary element of that span of the original dependent set, v1 through v sub n, but u was a completely arbitrary element of v sub n, which now allows us to say that the span of v1, v2 up to v minus 1 is the same as the span of our original set. And that's then sort of the end of that demonstration, or that proof. So we can throw out vectors if we have a linearly dependent set and not destroy the span behavior of that set of vectors. There's a couple of points that you should sort of pay attention to in chapter 2 relative to this linear dependence lemma. And one is actually labeled as a theorem, Theorem 2.6, and that says the following. In a finite dimensional, and this is really not a verbatim rewrite of Theorem 2.6, it's written a little bit differently, but in a finite dimensional vector space, we're going to look at two different lengths. the length of every spanning list, let's say of vectors, is greater than or equal to the length of every linearly independent list of vectors from that set. So a spanning list could include dependency among your vectors, and so the length of that might be pretty big. But if you now look at a subset of that or another list that's being used in your finite dimensional vector space, if you now have a linearly independent list, then that list is always going to be less than the length of every spanning list of vectors. Spanning list meaning it's spanning the entire finite dimensional space. So if that was n, let's say you had well, we haven't talked about dimensions, so maybe I shouldn't talk about that yet. But this hopefully is clear, but now we're trying to relate this notion of spanning list and linear independence. We could maybe have two vectors that are linearly independent, and maybe we're in R3, and we need at least three vectors to span that R3. But we could have a spanning list that had 5 different vectors in it. So the length of that spanning list might be 5. That's greater than or equal to 2 linearly independent vectors in that set. The most you're going to have in terms of linearly independent vectors in a 3-dimensional space is a set that's of size 3. Your spanning list is always going to be 3 or bigger in terms of number of vectors. That's what that theorem is saying. The other result or property is proposition 2.7. And this says that every subspace of a finite dimensional vector space is finite dimensional. That seems like you're maybe talking in circles, but every set, and we haven't even defined what we mean by dimension. But if we have a finite dimensional vector space, let's say it's 10, then every subspace of that 10-dimensional vector space is less than 10 or no greater than 10. It's finite dimensional also. That's really all that Prop 2.7 is saying. And so I would like to say that this makes sense intuitively. What we've talked about up to this point then is really span, vectors that span the entire set, and linear dependence and linear independence. Now we want to combine those concepts to create this notion of a basis of a vector space. So now let's look at the plural of a basis, and it's going to sound like I'm saying the same thing, and talk about bases. So now we have multiple basis sets, and this is from page 27 in Axler. A basis of a vector space V is a linearly independent list of vectors that spans V. Any set of vectors that are both linearly independent and they span V, you can use that list as a basis. And this is now, when you plural, take several basis sets, you have bases, B-A-S-E-S. So now we're on the topic of this concept of having different sets of basis vectors. But to find one set of basis vectors, it not only has to be linearly independent, there can be no dependency among those vectors, but that set of vectors has to span the entire space. The combination then allows you to use that as a basis of your vector space V. Here are some consequences of that concept. We can now talk about certain coordinates relative to a given basis of that vector set or vector space. So this now provides a coordinate system. And those coordinates, depending on your basis, may be different or will be different. But you can now have different coordinates representing, let's say, points or different combinations of vectors in your vector space. Another consequence is proposition 2.8, which says that any element of your vector space V can be built or is expressible as a unique linear combination of basis vectors. We can also talk about the length of the list of basis vectors is actually equal to the length of the shortest spanning list. I think before we talked about having spanning lists that could be 10, 11, 12, 13 in length. Well, if we have a set of basis vectors, then that set has to be linearly independent. And so that's going to be the minimum number of vectors in that list, which says that's corresponding to the shortest list of, or shortest length of your spanning list of vectors. And that's all based on this concept of linearly independent vectors, that length being less than or equal to the length of your spanning set. Meaning the length of the linearly independent list is less than or equal to the length of the spanning list. And since our basis vectors, or since the basis is both linearly independent and spanning, then we must have equality in that particular case. Question? Yes. So now this will become a little bit more clear when we start going through some examples, but provides a coordinate system if we had, well, maybe I'll wait until I get into some examples. But if we have multiple bases for a particular vector set or vector space, then we can actually define different combinations of those vectors in the basis set that represent exactly the same point. So you can now establish coordinates or combinations of your basis, and what that means is dependent on the basis set that you've started with, what those coordinate values represent. Typically, we're thinking in terms of our standard basis, where we have the x direction, the y direction, and the z direction, or we have vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's sort of how we're used to thinking. But you could have a different basis set, and that would then give rise to different coordinates or a different coordinate system for the same points in your three-dimensional space. That's what that's meaning. Now, that being said, we actually have a lot of potential sets of basis vectors. There's not one unique set, although we like to think in terms of the standard basis. But generally, there's no unique basis. Or maybe what I should say are there's many shortest spanning lists. Let's look at some examples, and maybe this will start to make it a little bit more concrete. Suppose that we start with our vector space V being something that I can easily maybe sketch, which is R2. And suppose now I say, okay, here is a collection of vectors in that set or in that vector space. Do those two vectors form a basis in R2? Yes or no? In this case, that is a basis because one, they're linearly independent, aren't they? If you simply sketched that, we have the first vector, which was right there, let's say 0, 1. The second vector, whoops, those are supposed to be the same length, that's 1, 0, and that fills up all of R2. You can find any linear combination of those two vectors and reach any point in terms of those two vectors linear combination. And this is actually our form that we call the standard basis, this particular choice of having all zeros except one in one of the coordinate locations. So this form is called the standard basis. What's another example? Suppose that I give you the set 1, 1 and minus 1, minus 3. Can we use that set of vectors as a basis? And if it's not making sense, we could say, well, let me just sketch those and see what I have. I now have there's the first vector, and now the second vector is minus 1, minus 3. That's down here. And what we want to then be asking is, any linear combination of these vectors, does that span the entire space? And really what we're asking is, are these vectors not aligned? And the answer is yes, they're a little bit off. They're not 90 degrees apart like our first one, which makes the standard basis nice, because this basis is orthogonal. This set is not, but it still forms a basis. These two vectors then, that set is a basis. It's not orthogonal, but it still forms a basis. And now you could say, okay, here's where we could then talk about a coordinate system. We could say, if you now want to represent the point in space right here, and now you'll have to use your imagination if all you're doing is listening, since you can't see this point unless I make it clear on the diagram. Now suppose that we want to make it to that point and represent that as a linear combination of our, maybe I didn't want to do that, but that's okay. So now, how do I make that point? Pardon? Just add them together. I now need to take 1 times the first vector plus 1 times the second vector. And so now my coordinates in this coordinate system, this point is 1, 1, meaning I have, let's say, A1 is equal to 1 and A sub 2 is equal to 1, meaning this point 1, 1 is now 1 times 0, 1 plus 1 times 1, 0. And my coordinates now, if I wanted to think of those, I could say A1, A2 is 1, 1. But now if I said, well, I want to get to the same point right there in this, in terms of this basis set, now what do I have? Let's say that I now have B1 times 1, 1 plus B sub 2 times minus 1, minus 3. Now I need just B1 to be 1 and B sub 2 to be 0, so that in this coordinate system, that same point in two-dimensional space is now 1, 0. So I could have two different coordinate systems resulting from two different bases in the same finite dimensional vector space. So that's what I mean by, what do I mean by a coordinate system? Now your coordinate system is going to be depending on how you've defined your basis vectors. So that 1, 0 here actually means this point. Whereas before, in this set of basis, I needed 1, 1 to represent that same point. Is that clear, or does that help answer that earlier question on coordinate system? Let's look at some more examples of combinations of vectors. Suppose that I give you a set 0, 1. And again, we're still working in R2. Is this set of vectors a basis? Hopefully it's clear that that's not. And the reason is I can't get to every point in that two-dimensional space. All I can get to are points in the y direction. Is that clear? So this doesn't span. So this fails being a basis because this doesn't span R2. Is that clear? So you can't get to that one point that we identified before, which was this point right here, which was 1, 1 in the standard basis. So I'll probably use the standard basis a lot in talking about different points in two-dimensional space. So there's no linear combination of 0, 1 that will get us to 1, 1. So that doesn't form a basis. What about the next set? Suppose that I give you the following set of vectors, 0, 1, 1, 0, and 1, 1. Is that a basis? Yes or no? Guess you can tell by my spacing. Left myself enough room to put the not in there. Why is this not a basis? I have this guy, I have this guy, and I also have that guy. But what did we say the requirements of a basis needed to be? We needed to have a linearly independent set of vectors that span all of R3. This makes a spanning list, doesn't it? And the length of that spanning list is 3. But it's not a basis because it's linearly dependent. Or points in R2 can be written non-uniquely as combinations of those 3 vectors. Questions on that? So those are 4 different examples. 2 were successful at forming a basis. The last 2 were not, and they failed for 2 different reasons. Let's now look at some theorems in Axler related to this concept of basis, spanning lists, and linearly independent vectors. Theorem 210. This says that every spanning list in a vector space can be reduced to a basis of the vector space. And this is now playing on the idea that you can have a spanning list that contains linearly dependent vectors. So every spanning list in a vector space can be reduced. You can throw away vectors until you find what? A set that's linearly independent, and then you have a basis. That's really what this is saying. If we wanted to try to justify that with a proof, then we could do the following. We could say, well, let's be given a list B of n vectors, v1 through v sub n. And let's say that that list spans V, but B, capital B, is not a basis. So if we have this set of vectors that spans all of V, but it's not a basis, then what must be going on? What's the definition of our basis telling us? If I say I'll give you a bunch of vectors in this set, and it spans your entire vector space, but it's not a basis, then what do you know has to be happening in that set of vectors? You must have some dependency among those vectors, right? They're not linearly independent. So by the definition of our basis vectors, B must be linearly dependent. Well, if we have linear dependency among vectors, then we can write some in terms of the others, can't we? From before, this linearly dependent list must contain at least one element or vector that we can write in terms of the others. That is expressible as a linear combination of the other vectors or other elements in that set B. So if we go back to our big lemma, which is this linear dependence lemma, what did that allow us to do? If we have a set of vectors that are linearly dependent, what can we do with that set and still preserve a given property of that set? Is that too vague, that question? So if I have a set of vectors that are linearly dependent, what can I do with that set and still preserve a property of that set? I can throw things out, can't I, and still preserve the span of that original set. That's what the linear dependence lemma allowed us to do. So from the linear dependence lemma, we can actually delete this dependent element without reducing or changing the span of the original list. We've now thrown out one of those. If we had n, now we have n minus 1 vectors in our set. Now B is reduced by 1 vector, that set of vectors. Now we could check and say, is this new list of vectors linearly independent? If it is, then we have a basis. If it's not, we just repeat the process. We find a vector that's linearly dependent, throw it away, and check the remaining vectors. So now, if the new list is linearly independent, we've built or created a basis by reducing that set of spanning vectors. Have created a basis of our vector space V, and we're done. If this new list, if the resulting list still has some dependencies, we just repeat the process that we just did. We find one that's linearly dependent, we throw it away, and then check to see if we have the remaining vectors linearly independent. If the resulting list is still linearly dependent, we repeat the process. So now we have a way of, if somebody gives us a spanning list, now we can create a basis from that spanning list. They don't have to give us a basis right away. They can just say, here's a bunch of vectors and they span your entire space. Good luck. Well, now we can pull from those and create a basis. That's what this is saying. It's saying maybe we have a huge tub of vectors. Well, we can get rid of the ones that are linearly dependent, only leaving the linearly independent ones, and create a basis from that set. That's the reduction process. We can go back to one of our earlier examples. It was the last example of those 4. We could take this list of 0, 1, 1, 0, 1, 1. Hopefully there's no argument that that actually spans all of R2. And it's not a basis because there's some linear dependency among those vectors. How would we create a basis from this set? So if this was our capital B, what would we want to do? Which one of those would you like to get rid of? Maybe this last one, the 1, 1, and just preserve the standard basis. So if we delete or if we select 1, 1, then we're left with this new list. That's linearly independent, and it spans all of R2. Now we have a basis from starting with something that wasn't a basis. It was a spanning list, and that was too many vectors. That length was too long. Questions on that? Let's step through some more of these properties in Axler, and the next one is corollary, which is maybe not quite the level of a theorem. But corollary 211, this says that every finite dimensional vector space has a basis. That's sort of a nice property. If now somebody gives you a finite dimensional vector space, which may be R3, it might be a set of polynomials, it may be something else that we've created that forms a vector space. If it's finite dimensional, then we can find a basis for that vector space. So any or every finite dimensional vector space has a basis. As a proof, by definition, every finite dimensional vector space can be spanned, can it? It has a spanning list. That's the definition of being finite dimensional. So we now have a spanning list if we have a finite dimensional vector space. Somebody can throw us a bunch of vectors and say, oh, this will span your entire finite dimensional vector space. But once we have a spanning list, we can go back to the earlier theorem and say, oh, I can throw things out of there to get you a basis. So once you have a spanning list, you're good to go in terms of creating a basis, in theory. Yes. So now the question was, if we have, I think, let me rephrase what I thought I heard. Let's say we're dealing with R2, and now you said, what if I give you the vector 4, 5? Is that vector linearly independent? That's the only vector you gave me. So now you've given me one set, and that set contains one vector, and it's in this two-dimensional space. Is that vector linearly independent? What do you think? Yes. So that vector 4, 5 is linearly independent. Now suppose I give you 4, 5, and 8, 10. Two vectors in a set. Is that set of vectors linearly independent? No, they're aligned, aren't they? But if I gave you 4, 5, and 1, 0, those are linearly independent. They're not aligned. Do they span all of R2? Yes. So that would form a basis. It's not the standard basis, so you're going to get some weird coordinates, but it's fine. You can still get to any place in R2 by a linear combination of 4, 5, and 1, 0. No. So the vector 4, 5 by itself is linearly independent, but it didn't span all of R2, did it? So if you give me 4, 5 as a vector, I can give you a point, many, many points that you can't get to by scaling that vector 4, 5. I could give you the point 1, 0 in the x direction, and you can't get there by a linear combination of 4, 5. So that fails as being a basis because it's not spanning the entire two-dimensional plane. Is that making sense? So it is linearly independent, but it's not spanning. So you need both of those pieces to form a basis. You need linearly independent vectors and those vectors spanning the entire space. Where was I? Oh, I was throwing things away, right? I need to do this in my office. You guys haven't seen my office, which is maybe a good thing. But well, never mind. I have a spanning set in the office. I just need to throw things away and just come down to a linearly independent set. But here we just proved a basis can be generated. And it's really not generated, it's produced. We're throwing things away, aren't we, to produce it from a spanning set. So can be generated from any spanning list. So that's starting with one of the properties of the two that we need to form a basis. And that one started with a spanning set. Why don't we think about another theorem that starts with the other property? What if we have a set of linearly independent vectors? Then what are we going to do? Now we are going to build. We're going to add new linearly independent vectors to create a basis so that we can span the entire set. And this is now Theorem 212. This theorem says and this is what I just did to the previous question, actually. We started with 4, 5, and we build up a basis from 4, 5. And that's what this theorem says we can do. So Theorem 212 says every linearly independent list of vectors in a finite dimensional vector space now we're extending and not reducing. Now we're building up from linearly independent. Can be extended to a basis. What's our proof? Suppose we're given a linearly independent list B of vectors in V that are not a basis of V. Suppose B is now this set V1, V2, up to V sub n. Now we're failing being a basis for what reason? Well, you're giving me a set of linearly independent vectors. Why isn't that a basis? You gave me 4, 5, didn't you? And what did we conclude? If we're in a two-dimensional space, that doesn't span all that two-dimensional space, does it? So you can give me vectors that are linearly independent, but if they don't yet span the space, then it's not going to be a basis. So this is failing being a basis because it's maybe not spanning the entire space. We were told it's not a basis, so They're linearly independent. The only way it can fail being a basis is it must not be enough to completely span the space. From the definition of a basis, B must not span V. All right, if it doesn't, then let's go find a vector that's in V, but not yet in B. So let's select an element. Let's say that's U, that's in V, such that U is outside of the span of B. Is that clear? So now we go pick an element in the vector space that's not in the span of B, our original set of linearly independent vectors. So if we were dealing with R3, here in very basic terms, and somebody gives you the x-axis and somebody gives you the y-axis, it's pretty easy which vector to pull, isn't it? Or to pick. We could take the z direction, and that would not be in the span of B. So now let's form a linear combination of u's and v's. So if we form a linear combination, u, that's v1 plus v2 plus vn plus something we don't yet know. Let's say it's q. Well, that's like an algebra problem, except now it's maybe a vector, but we can solve for that unknown q, can't we? Somebody's picked a u, we were given all the v's, we can solve for q. Q is now u minus v1 minus v2 minus v sub n. Now, is q okay? Are we okay with what q ends up being? That seems, what do we want it to be? Q better be in our vector space, is it? What's the definition of a vector space? What do we know one of the properties of a vector space is? It's closed under addition, isn't it? And what are we doing? U was in V. All of these V's were in B, or were in V, which was in B. And so all of these linear combinations allow Q to be in V, because V was closed under addition. So Q is in our vector space because of the property of a vector space. V is closed under vector addition. Now we can use that Q to build up our set. Now we're constructing, we're growing this linearly independent set of vectors. So we add Q, maybe I should say to the list B. So that now B, this is like some MATLAB routine where we just keep adding on. We just concatenate it onto the tail of a vector. We just keep growing this list. We now have B defined to be V1, V2, V sub n, and Q. Now what would be nice? It'd be nice if B now spans all of the space, wouldn't it? Then we would be done. If it doesn't, then we just repeat the process. We pick another Q. Let's call it Q sub 1. Throw that into B, and now we have something that's spanning more of the space. Maybe we weren't very judicious in our choice of U in the first time that we were trying to pick a new element in V. So now we have B. If B now spans V, that's going to give us a basis of this vector space V, and we're done. If B does not span V, then we just continue this process. We pick a new U that's not in B and keep going. Let's just put this into an example so that we can make sure that we're all on the same page with this idea of now building up from a linearly independent set of vectors. Now we're building a basis from a linearly independent set of vectors. Suppose B is now 1, 0, 0, and 0, 1, 0. And our vector space is R3. Now there's all sorts of choices, but maybe for whatever reason I say, you know what, let me pick U to be 5, 6, and 8 for whatever reason, but I know that that's in V and it's not in B, is it? So now I can find that U is this 5, 6, and 8, and I want that to be 1, 0, 0 plus 0, 1, 0. That's my B plus some Q. And if I do the algebra and just remove the B's, I end up with Q1, Q2, and Q3 being 4, 5, and 8, which is an element of V, and now my B is 1, 0, 0, 0, 1, 0, and 4, 5, 8, and I now know that span of B is all of R3, and I've built up the basis that I need from a set of linearly independent vectors. They're not orthogonal, which may be an issue, but it's still a basis. And it may give me a weird coordinate system, but it's still a basis. Let's do one more proposition. Prop 213. Suppose we're given a finite dimensional vector space V and a subspace of that V U. then we can actually say that there exists another subspace, which we can call W, such that the direct sum of U and W spans V. And I'll just let you look at Axler on pages 30 and 31 for the proof of that result. But what that really says is that any vector space is decomposable as a direct sum of subspaces. And if you're always at a loss, how do I do that? Well, sometimes the extremes are an easy way to generate such a decomposition. Maybe the trivial set. By that, I mean we could select V to be the additive identity plus V itself. And that's then one way to decompose a vector space into two different subspaces. And those are the two limiting subspaces of V. I may give you a little bit more on dimension before we meet on Wednesday, so you might stay tuned to the website and see if I give you a little bit more so that we can kind of move through the material. I'll see you on Wednesday.